Hello everyone. Let's review from the second exam today. First problem, consider a set S. S has elements -5, -1, 0, 3, 4, 7, and 10. Where the number is randomly chosen from S, let the random variable x represent the value of the chosen number. Find each of the following probabilities. Part A, the probability that x is 0. Part B, the probability that x is less or equal to 0. Part C, probability that x is odd, given that x is greater than 0. Part D, probability that x is greater than 0, given that x is even. So, first of all, let's set out the problem first. Here, since we choose a number randomly from the set, that means every number has the same chance to be chosen. This x is a uniform distribution. This x is a uniform distribution, and its discrete uniform. It's discrete uniform over the set S. Next, write down the probability function, f of x. Since every number has the same chance to be chosen, there are 7 numbers on the set, so the chance for each number is 1 over 7. The chance for each x in the set is 1 over 7. Support. Next, the support. Support is the set of all possible value of x. Support is the set of all possible value of x. Since we choose a value from the set, x is the value of all elements in the set. -5, -1, 0, 3, 4, 7, and 10. So that's the setup of the problem. Next, answer the questions based on the setup here. Part A, what's the probability that s equal to 0? S equal to 0. 0 is in the support. 0 is in the support. So we have f of 0. F of 0 is 1 over 7. Part B, what's the probability that x is less than or equal to 0? If x is less or equal to 0, support here is 0, -1, and -5. That's the support. X is less or equal to 0. S must be 0, -1, -5. And we know that probability for each number is 1 over 7. Part C, what's the probability that x is odd? Such that x is greater than 0. What's the probability that s is odd and s is greater than 0? This is conditional probability. This is conditional probability. This can be written as probability that x is odd and s is greater than 0 over the probability that s is greater than 0. This is conditional probability. On the numerator, x is odd and s is greater than 0. In the support, s is odd, s is greater than 0. It's either 3 or 7. We have f of 3 plus f of 7. In the denominator, s is greater than 0. If s is greater than 0, we have 3, 4, 7, 10. F of 3 plus f of 4 plus f of 7 plus f of 10. That's 1 over 7 plus 1 over 7. 1 over 7 plus 1 over 7 plus 1 over 7, which is 2 over 7 over 4 over 7, which is half. Part D, what's the probability that s is greater than 0 given that x is even? Again, this is conditional probability. It can be written as probability that x is greater than 0 and x is even over the probability that x is even. Then on the numerator, probability that s is greater than 0 and s is even. If s is greater than 0 and s is even, it must be 4 and 10. In the denominator, x is even. If s is even, s could be 0, 4, and 10. Then f of 4 is 1 over 7, f of 10 is 1 over 7. In the denominator, f of 0 is 1 over 7, f of 4 is 1 over 7, f of 10 is 1 over 7, which is 2 over 7 over 3 over 7. Together is 2 over 3. Number 2, in a college, 10% of the students come from foreign countries. A group of 30 students are randomly chosen from the college. Part A, what's the probability that there are exactly 5 foreign students? Part B, what's the probability that there are at least 2 foreign students? Part C, use Poisson distribution to approximate the answer to part A. So let's first of all decide what kind of probability distribution it is, and then set down a problem. In a college, 10% of the students come from foreign countries. A group of 30 students are randomly chosen from the college. When we choose a student from the college, the student is either foreign student or non-foreign student. And choosing 30 students we can consider there are 30 trials. So we can consider this is a binomial distribution. The x represent, then the random variable x represent the number of chosen foreign students. Then the random variable x represent the number of chosen foreign students. Then x has a binomial distribution. N is 30 because we are choosing 30 students, consider there are 30 trials. P is 10%. Every time when we choose a student, there's 10% chance to get a foreign student. And the chance for every choice is the same. The chance for every trial is the same. This is P, 10%. Next, write down the formula. Probability for binomial distribution is, the formula for binomial distribution is n choose x, p to the power of x, times 1 minus p to the power of n minus x. That's the probability function for binomial distribution. And here, now we're plotting n and p. N is 30, p is 10, 10%, 0.10. N is 30, p is 10%. One minus p is 90%, that's 0.90. To the power of n minus x, n is 30. So this is the probability function. Next, find the support. For binomial distribution, support is integers from 0 to n. For binomial distributions, support is the integers from 0 to n. So x could be 0, 1, 2, up to n. Here n is 30. So here, that's the probability function. That's the support. Then, based on this, answer the question. Part A. What's the probability that there are exactly 5 foreign students? What's the probability that s equal to 5? For s equal to 5, we have f of 5. For f of 5, plug in 5 for x. 30 choose 5. 0.10 to the power of 5. 0.90 to the 30 minus 5 is 25. Then type this to the calculator. Here I use my calculator, I get 0.1023. That's part A. Part B. What's the probability that there are at least 2 falling students? For part B, we're looking for probability that x is greater than or equal to 5. So greater than or equal to 2, at least 2. S is greater than or equal to 2. If we try to find probability that s is greater or equal to 2, s could be 2, 3, 4, 5, up to 30. There may be too many terms, too much work. To make it a little easier, think of the complement. Probability that x greater or equal to 2, I can write it as 1 minus probability that x is less than 2. When s is less than 2, s could be either 0 or 1. When s is less than 2, s could be either 0 or 1. I have f of 0 plus f of 1. Then for f of 0, plug in 0 for x. I have 30 choose 0, 0.10 to the power of 0, 0.90 to the power of 30 minus 0 is 30. Plus f of 1. For f of 1, plug in 1 for x. It's 30 choose 1. 0.10 to the power of 1. 0.90 to the power of 30 minus 1 is 29. Then here, use calculator. I use calculator, I get 0.8163. Part C. Part C. Use Poisson distribution to approximate the answer to part A. When we use Poisson distribution to approximate answer to approximate binomial distribution, lambda is n times p. When we use Poisson distribution to approximate a binomial distribution, lambda is m times p. N times p here. N is 30. P is 0.10. So n times p is 30 times 0.10, which is 3. Lambda is 3. That means on average, when we choose 30 students, we expect to have 3 falling students. On average, when we choose 30 students, we expect to have 3 falling students. So here, same thing, let x represent the number of chosen falling students. Then we use Poisson distribution to approximate binomial distribution. Here x has a Poisson distribution. Lambda equal to 3. On average, we expect to have 3 falling students when we choose 30 students. Next, write down the probability function. For Poisson distribution, the probability function is f of x equal to e raised to negative lambda, lambda to the power of x over s factorial. Plug in lambda. Here, lambda is 3. Plug in lambda. Plug in 3 for lambda. Plug in 3 for both lambda. I have e raised to negative 3 times 3 to the power of x. That's the probability function. Next, the support. Find the probability function and the support of x. Support of x. For Poisson distribution, support is the set of all integers from 0 to infinity. Support is the set of all integers from 0 to infinity. I have 0, 1, 2 up to infinity. Then, in part A, what we are looking for is what's the probability that there are exactly 5 falling students. In part A, we are looking for probability that x equal to 5. Plug in 5 for x. E raised to negative 3 times 3 to the power of 5 over 5 factorial. Then use calculator. Here I get 0.100A. That's an approximate answer to part A. That's an approximate answer to part A. Number 3. A lake contains 400 fish, and 100 of them are tagged by scientists. A researcher randomly catches 20 fishes from the lake. Part A. What's the probability that there are exactly 7 tagged fish? Part B. What's the probability that the number of tagged fish is between 4 and 6? Part C. Use binomial distribution to approximate answer to part A. So, first of all, let's decide what kind of probability distribution it is, then set down the problem. A lake contains 400 fishes. 100 of them are tagged by scientists. A researcher randomly catches 20 fishes from the lake. And we are looking for probability about tagged fishes. We know that every time when we catch a fish, the chance of getting tagged fish is different, since we don't replace the fish back. Since when we catch a fish, we don't replace it back. So every time when we catch a fish, the chance of getting tagged fish is different. So here we can think of hypergeometric distribution. Let x represent, then random variable x represent the number of caught fish, the number of caught fish which are tagged. Then x has a hypergeometric distribution. Since we are looking for probability about tagged fishes, we can consider the number of tagged fishes represent successors. So we have 100 successors here, 100 success here. The other fishes are considered failures. The other fishes are considered failures. 400 minus 100, there are 300 failures. And we are catching 20 fishes, so n is 20. Number of trial, we are catching 20 fishes, n is 20. Next, write down the formula. Write down the probability function for hypergeometric distribution. The probability function for hypergeometric distribution is n1 choose x, n2 choose n minus x, n1 plus n2 choose n. That's the formula for hypergeometric distribution. Then we can plug in n1, n2, and n. n1 is 100, n2 is 300, n is 20. On the denominator, n1 plus n2, 100 plus 300 is 400. Choose n is 20. That's the probability function. Next, find the support. To find the support, we first of all compute the maximum of 0 and m minus n2. We first of all compute the maximum of 0 and m minus n2. M minus n2 here is 20 minus 300, which is negative 280. M minus n2, 20 minus 300, which is negative 280. And the maximum of 0 and negative 280 is 0. Next, we try to find the minimum of n and n1. N is 20, n1 is 100. Minimum of 20 and 100 is 20. So the support of x is the set of all integers from 0 to 20. That's the setup. Next, based on this, answer the question. Part A. What's the probability that there are exactly 7 tagged fishes? We're looking for probability that s equal to 7. We plug in 7 for x. We have f of 7. Probability that s equal to 7 is f of 7. We plug in 7 for x. That's 100 choose 7 times 300 choose 20 minus 7 is 13 over 400 choose 20. Then use calculator. Here I get 0.1129. Part B. What's the probability that the number of tagged fish is between 4 and 6? Between 4 and 6, if we don't specify it's inclusive or exclusive, we include both 4 and 6. For between 4 and 6, if the problem doesn't specify, we include 4, include 6. So that's the probability that x is between 4 and 6, including 4 and 6. If the problem doesn't specify, we include 4 and 6. 4 and 6 is in the support. So we have f of 4 plus f of 5 plus f of 6. For f of 4, we plug in 4 for x. Plug in 4 for x. 100 choose 4. 300 choose 20 minus 4 is 16. Over 400 choose 20. Plus f of 5. F of 5 plug in 5 for x. That's 100 of 5. 100 choose 5 times 300 choose 20 minus 5 is 15 over 400 choose 20 plus f of 6. 100 choose 6. 300 choose 20 minus 6 is 14 over 400 choose 20. Then use calculator. Here I use my calculator. I get 0.5725. That's part B. Part C. Use binomial distribution to approximate the answer to part A. Part C. Use binomial distribution to approximate the answer to part A. When we use binomial distribution to approximate hypergeometric distribution, n stays the same. N stays the same. I let P equal to n1 over n1 plus n2. When we use binomial distribution to approximate hypergeometric distribution, I let P equal to n1 over n1 plus n2. The number of viewable outcome divided by number of all possible outcome. Then n1 here is 100. n1 plus n2 is 400. 100 over 400 is 1 over 4. That means when we catch a fish, the chance of getting tagged fish is 1 over 4. The chance of getting a tagged fish is about 1 over 4. Then let x represent the number of caught fishes which are tagged. Number of caught tagged fishes. Let x represent the number of caught tagged fishes. Then x has approximately a binomial distribution. It's an approximation. X has approximately a binomial distribution. Here, n is 30, n stays the same, n is 20, n stays the same, n is 20. P is 1 over 4. Then use the formula. The probability function for binomial distribution is n choose x, p to the power of x, 1 minus p to the power of n minus x. Here n is 20, x is x, p is 1 over 4 to the power of x. 1 minus p, 1 minus 1 over 4 is 3 over 4 to the power of m minus x. And the support of x, For binomial distribution, support of x is the integers, all integers from 0 to n. 0, 1, 2, up to 20. That's the support. Then answer the question for part A. Use this formula and the support. Answer the question for part A. Part A. What's the probability that there are exactly 7 tagged fishes? We are looking for a probability that s equal to 7, which is f of 7. We plug in 7. We plug in 7 for x. We have n to 7, 20 to 7, p to the power of 7, 1 over 4 to the power of 7, times 3 over 4 to the power of 20 minus 7 is 13. Here. We plug in 7 for each x. Plug in 7 for each x. N is 20. Plug in 7 for each x. That's what I get here. Then use calculator. Here I use my calculator, I get about 0.1124. That's an approximate answer to part A. That's an approximate answer to part A. Number 4. In a restaurant, hamburgers are sold at an average rate of 20 per hour. Part A. What's the probability that at most 2 hamburgers are sold in a given 9 minutes? Part B. What's the probability that no hamburgers are sold in the first 6 minutes? Part C. Redo part B using exponential distribution. First of all, let's decide what kind of probability distribution it is. Then solve the problem. In a restaurant, hamburgers are sold at an average rate of 20 per hour. Consider selling a hamburger is an event. The problem is telling that the event occurs on average 20 times per hour. The event occurs on average 20 times per hour. If we know the average number of occurrence of an event, we can use Poisson distribution. If we know the average number of occurrence of an event, we can use Poisson distribution. Part A. What's the probability that at most 2 hamburgers are sold in a given 9 minutes? What's the probability that at most 2 hamburgers are sold in a given 9 minutes? We know that on average, we expect to sell 20 hamburgers in 60 minutes in an hour. How many hamburgers do we expect to sell in 9 minutes? How many hamburgers do we expect to sell in 9 minutes? I can cross multiply and solve this equation for lambda. 60 lambda equal to 180. Lambda equal to 3. That means in 9 minutes, in a given 9 minutes, we expect to sell 3 hamburgers on average. In a given 9 minutes, we expect to sell 9 hamburgers. We expect to sell 3 hamburgers on average. So lambda is 3. Here, let x represent. Let the London variable x represent the number of sold hamburgers in a given 9 minutes. Then x has a Poisson distribution with lambda equal to 3. Next, write down the probability function. For Poisson distribution, the probability function is e raised to negative lambda, lambda to the power of x over x factorial. Plug in lambda. Lambda is 3. That's the probability function. Next, find the support of x. For Poisson distribution, support of x is the set of all integers from 0 to infinity. The set of all integers from 0 to infinity. Then, based on this, answer the question. What's the probability that at most 2 hamburgers are sold in a given 9 minutes? At most 2 means probability that x is less than or equal to 2. What's the probability that at most 2 hamburgers are sold in a given 9 minutes. At most 2 means x is less than or equal to 2. That's f of 0 plus f of 1 plus f of 2. Then for f of 0, plug in 0 for x. For f of 1, plug in 1 for x. For f of 2, plug in 2 for x. I have e to the power of negative 3 times 3 to the power of 0 over 0 factorial. E to the negative 3 times 3 to the power of 1 over 1 factorial plus e to the power of negative 3 times 3 to the power of 2 over 2 factorial. Then use calculator. I get 0.4232. Use calculator, I get 0.4232. That's the probability that at most 2 hamburgers are sold in a given 9 minutes. Now part B. What's the probability that no hamburgers are sold in the first 6 minutes? What's the probability that no hamburgers sold in the first 6 minutes? So we know that hamburgers are sold in a rate of 20 per hour, 20 hamburgers per hour. We try to find out in 6 minutes how many hamburgers do we expect to sell. We try to find the number of hamburgers we expect to sell in 6 minutes on average. So we can sell 20 hamburgers in 60 minutes. We try to find out on average how many hamburgers we can sell in 6 minutes. Here we can cross multiply. I can cross multiply, solve an equation for lambda. We know 60 lambda is 120. Lambda equal to 2. That means on average, in 60 minutes, we expect to sell 2 hamburgers. This lambda means on average, we expect to sell 2 hamburgers in the first 6 minutes. So here, the x represent the number of sold hamburgers. In the first 6 minutes. Then, since we know the average number of occurrence of an event, we can use Poisson distribution. Since we know we can sell hamburger on average 2 hamburgers in 60 minutes. On average, we can sell 2 hamburgers in 6 minutes. That means on average, the event occurs twice in the time period. We can use Poisson distribution. X is the Poisson distribution with lambda equal to 2. Then write down the probability function. The probability function is e raised to negative lambda times lambda to the power of x over s factorial. Plug in lambda, e to the power of negative 2 times 2 to the power of x over x factorial. That's the probability function. Next, find the support. For Poisson distribution, support is the set of all integers from 0 to infinity. For Poisson distribution, support is the set of all integers from 0 to infinity. We are looking for the probability that no hamburgers are sold in the first 6 minutes. That means probability that s equal to 0. No hamburgers are sold in the first 60 minutes. Probability of s equal to 0. That's f of 0. Since 0 is in the support. We have f of 0. For f of 0, plug in 0 for x. E raised to negative 2 times 2 to the power of 0 over 0 factorial. And we know that 2 to the power of 0 is 1. 0 factorial is also 1. And so it's e raised to negative 2. E raised to negative 2, if I use my calculator, it's about 0.1353. Part C. Redo part B using exponential distribution. If we try to use exponential distribution, we must know the average waiting time for the occurrence of an event. Consider selling a hamburger is an event. here event occurs 20 times per hour on average. The event occurs 20 times per hour on average. We try to find out how long do we have to wait for the occurrence of one event. So we know that we expect to sell 20 hamburgers in every 60 minutes on average. We try to find out how long do we have to wait to sell one hamburger on average. We try to find out how long do we have to wait to sell one hamburger on average. If I cross multiply and solve for theta, I have 20 theta equal to 60. Then theta equal to 3. That means on average, we expect to wait 3 minutes. On average, we expect to wait 3 minutes to sell one hamburger. On average, we expect to wait 3 minutes to sell one hamburger. That's what needs 3 minutes. Here, the x represents the waiting time. To sell the first hamburger. The x represents the waiting time to sell the first hamburger. Since we know the average waiting time for to sell hamburgers, that's an exponential distribution. X has an exponential distribution. Where theta equal to 3. The formula for exponential distribution is the probability density function, the PDF for exponential distribution is 1 over theta times e raised to negative x over theta if x is greater than or equal to 0 and 0 otherwise. Then we plug in 3 for each theta. Plug in 3 for each theta. Plug in 3 for each theta. That's the PDF. That's the probability function of x. That's the probability density function of x. That's the PDF of x. Next, for the support of x. For exponential distribution, support of x is the set of all integers, the set of all real numbers from 0 to infinity. For exponential distribution, support of x is from 0 to infinity, all real numbers from 0 to infinity. Then, based on this, answer the question. Redo part B using exponential distribution. What's the probability that no hamburgers are sold in the first 60 minutes? If no hamburgers are sold in the first 60 minutes, means the waiting time to sell the first hamburger is more than 6 minutes. If no hamburgers are sold in the first 60 minutes, that means the waiting time to sell the first hamburger is more than 6 minutes. If no hamburgers are sold in the first 6 minutes, that means the waiting time to sell the first hamburger is more than 6 minutes. So take integral for probability density function from the PDF. We take integral from 6 to infinity because we use area under the curve represent probability. Because we use area under the curve represent probability. So take integral from 6 to infinity. S is greater than 0. So take integral from 6 to infinity. F of x dx. And for x from 6 to infinity, x is greater than 0. So we use f of x equal to 1 over 3 times e raised to x over 3. We use f of x equal to 1 over 3 times e raised to negative x over 3 dx. Then take antiderivative. I get negative e raised to negative x over 3 from 6 to infinity. If I plug infinity, e raised to negative infinity is 0. If I plug in 6, I get e raised to negative 6 over 3. Double negative is positive. 6 over 3 is 2, so I get e raised to negative 2. If I use calculator, e raised to negative 2 is about 0.1353. So that's an answer, which is exactly the same as what we get in part B. That's exactly the same as what we get in part B. Number 5. Jerry is a college student, and he lives far away from school. His first class starts at 7:45 every Monday morning. Assume his arriving time is uniformly distributed from 7 to 8 a.m. In a random Monday morning, find each of the following probabilities. Part A. What's the probability that Jerry is late for class? Part B. What's the probability that Jerry arrives to class exactly at 7:45 a.m.? Part C. If it's known that Jerry didn't arrive at 7 a.m., at 7:30 a.m., what's the probability that Jerry will arrive class on time? So first of all, let's decide what kind of probability distribution it is. We know that Jerry's arriving time is uniformly distributed from 7 to 8 a.m. So we can consider this is a continuous uniform distribution. This is a continuous uniform distribution because the time is continuous. So we can consider this is a continuous uniform distribution. Let x represent, then a continuous random variable x represent Jerry's arriving time. Let's measure the arriving time in minutes. Measured in minutes. After 7 a.m. Then x has a uniform distribution. X has a continuous uniform distribution. From 0 to 60. From 7 to 8 a.m. At 7 a.m. it's 0. At 8 a.m. it's 60. Measured in minutes. From 0 to 60. Next, write down the formula. Write down the probability density function. What's the PDF of x? The PDF for continuous uniform distribution is 1 over beta minus alpha if x is between alpha and beta, and it's 0 otherwise. That's the formula for continuous uniform distribution. Here, alpha is 0, beta is 60. Alpha is 0, beta is 60. So I plug in 0 for alpha, plug in 60 for beta. Beta minus alpha, 60 minus 0 is 60. Alpha is 0, beta is 60. Support. What's the support of x? For continuous uniform distribution, support of x is the closed interval from alpha to beta. For continuous uniform distribution, support of x is the closed interval from 0 to 0 from alpha to beta, which is from 0 to 60. Then based on this, answer the question. Part A. What's the probability that Jerry is late for class? If Jerry is late, means he comes after 7:45. Since the class starts at 7:45. If Jerry is late, means he comes after 7:45. Means his arriving time is more than 45 minutes after 7. His arriving time is more than 45 minutes after 7. Then since this is x is a continuous random variable, we use integrals. Use area under the curve to represent probabilities. So take integral. Since x is a continuous random variable, we use area under the curve to represent probabilities. So here I take integral. Support is from 0 to 60. Support is from 0 to 60. So if x is more than 45, it's an integral from 45 to 60. Since the support is from 0 to 60. If x is more than 45, then we take integral from 45 to 60. F of x dx. When x is between 45 and 60, x is between 0 and 60. So I let f of x equal to 1 over 60. When x is between 45 and 60, it satisfies that x is between 0 and 60. So we use f of x equal to 1 over 60. Take antiderivative. We get 1 over 60x. Evaluate from 45 to 60. If I plug in 60, I get 60 over 60. If I plug in 45, I get 45 over 60. That's 15 over 60, which is 1 over 4. Part B. What's the probability that Jerry arrived class exactly at 7:45 a.m.? What's the probability that Jerry arrived class exactly at 7:45 a.m.? That means the probability that S equal to 45, exactly at 7:45, which is integral from 45 to 45, f of x dx. We know that for any continuous non-variable, probability that S equal to a constant is always 0. For any continuous non-variable, probability that S equal to a constant is always 0. Part C. If it's known that Jerry didn't arrive at 7:30 a.m., if it's known that Jerry didn't arrive at 7:30 a.m., let me see, count after 7:30 a.m. If it's known that Jerry count after 7:30 a.m., what's the probability that Jerry will arrive class on time? If he arrives class on time, means he come before 7:45. He come at 7:45 or before 7:45. So this is conditional probability. If it's known that Jerry did not arrive at 7:30, means he come after 7:30. What's the probability that Jerry come to class on time? If he come to class on time, that means he arrived at 7:45 or before 7:45. So x must be less than or equal to 45. So x must be less than or equal to 45. This is conditional probability. So denominator is probability that x is greater than 30. That's the denominator. Numerator is that x is less than or equal to 45 and x is greater than 30. We must consider both. X is less than or equal to 45 and x is greater than 30. That means x is between 30 and 45, including 45. X is less than or equal to 45 and x is greater than 30. That's a numerator. Then since x is a continuous non-variable, we use area under the curve to represent probabilities. So take integral from the top from 30 to 45, f of x dx. On the bottom, since support is from 0 to 60, if s is greater than 30, take integral from 30 to 60. Since support is from 0 to 60, if s is greater than 30, take integral from 30 to 60. Then we know that when s is between 30 and 45, it satisfies that s is between 0 and 60. So we use f of x equal to 1 over 60. Denominator, same thing. When s is between 30 and 60, it satisfies that x is between 0 and 60. So we use f of x equal to 1 over 60. Then take integral for the numerator and denominator. In the numerator, I get 1 over 4. In the denominator, I get 1 over 2. 1 over 4 over 1 over 2 is 1 over 2. Number 6. In a country, a historical record shows that earthquake occurs at an average rate of every 200 years. Assume there was an earthquake in the year 2014. Part A. What's the probability that there will be another earthquake within the same century? Part B. What's the probability that there won't be another earthquake until the 23rd century? First of all, let's decide what kind of probability distribution we can use. If we know the average waiting time of occurrence of an event, we can use exponential distribution. Here, in this problem, we know that on average, earthquake occurs every 200 years. On average, earthquakes occurred every 200 years. That means, on average, we wait 200 years for earthquake. On average, we wait 200 years for earthquake. So if we know the average waiting time for occurrence of an event, we can use exponential distribution. So here, let the continuous non-variable x. Let the continuous non-variable x represent the waiting time for the occurrence of the next earthquake. Then x has an exponential distribution. Since we know the average waiting time is 200 years, average waiting time for the occurrence of earthquakes is 200 years. Next, write down the formula. What's the PDF? The probability density function for exponential distribution is 1 over theta e raised to negative x over theta if theta is greater than or equal to 0 and 0 otherwise. If x is greater than or equal to 0, and 0 otherwise. Next, plug in 200 for theta. Plug in 200 for theta. Theta is 200. Plug in 200 for each theta. So I have 1 over 200 e to the power of negative x over 200. That's a PDF. That's the probability density function for x. And the support of x. For exponential distribution, support of x is the set of all real numbers from 0 to infinity. For exponential distribution, support is the set of all real numbers from 0 to infinity. Then, based on this, answer the question. Part A. What's the probability that there will be another earthquake within the same century? That means the waiting time is, what's the probability that there will be another earthquake within the same century? Now, for century, let me clear a few things. For century, let's make a few things clear. What's the first century? First century is the year from year 1 to up to 100. That's the first century. What's the second century? Second century is the year 101, 102 to the year 200. That's the second century. There's no year 0. So first century is the first 100 years from 1 to 100. There's no year 0. The year is for -2, -1 BC. After -1 is 1 AD. Year 1, year 2, and so on. There's no year 0. So the first 100 years is from year 1 to 100 AD. Second century is the year 101 to 200 AD. Currently, we are in the 21st century. So far, we are in the 21st century. 21st century is the year 2000. So 2001, start from 1. 2001 to 2002 until 2100. That's the 21st century. 22nd century is the year 2101, 2102 until 2200. That's the 22nd century. 23rd century is the year start from 2201, 2202 to the year 2300 AD. Now, part A is asking, what's the probability that there will be another earthquake within the same century? Means the next event occurs before the year 2021. Let me draw a timeline here. (2014), that's 2015, 2016, and the end of the century is 2100. That's the 21st century. 22nd century starts 2101, 2102, and so on. That's the 22nd century. We're looking for probability that another earthquake within the same century means another earthquake before the year 2101. Another earthquake before the year 2101. So last earthquake occurs in the year 2014. That's time equal t equal 0. T equal 1. So at the end of 2100, take 2100 minus 2014. T is 86 here. At the end of 2100, that's December 31st, 2100. That's December 31st, 2100. T equal 86 here. Here T is 1. 2015 minus 2014, I get 1 here. Here 2100 minus 2014, I get T equal 86. So what we want is next earthquake occurs before the year 2100. That's the probability that the waiting time is less than 86 years. That's the probability that the waiting time is less than 86 years. If an earthquake occurs in the same century, that means the waiting time is less than 86 years. If an earthquake occurs in the same century, that means the waiting time is less than 86 years. It's less than 86 years. So that's the probability that x less than 86. Then since x is a continuous random variable, we use area under the curve to represent the probability. Take integral. Suppose from 0 to infinity. If x is less than 86, take integral from 0 to 86. Suppose from 0 to infinity. If s is less than 86, take integral from 0 to 86. Then the waiting time for the next earthquake is less than 86. If the waiting time is less than 86 years, means the earthquake occurs somewhere here within the same century. Then take integral 1 over f of x dx. First polar f of x dx. Then for x between 0 and 86, s is greater than 0. It satisfies that s is greater than 0. So use this function. F of x equal to 1 over 200 e raised to negative x over 200. Dx. Then take antiderivative. That's negative e raised to negative x over 200. Evaluate from 0 to 86. If we plug in 86, I get negative e raised to negative 86 over 200. If we plug in 0, e raised to 0 is 1. So the answer can be written as 1 minus e raised to negative 86 over 200. Then use calculator for the answer. Here I use my calculator, I get 0.3495. Here we got 0.3495. Part B. Number 6, part B. What's the probability that there won't be another earthquake until the 23rd century? What's the probability that there won't be another earthquake until the 23rd century? 23rd century. start in the year 2201. So that's the year 2200. That's the end of 22nd century. '23rd century started in the year 2201, and so on. What's T here? What's T here? This T is at the end of 2200, in the beginning of 2201. So we know that when T is 1, in the year at the end of 2015, T is 1. 2015 minus 2014 is 1 here. At the end of 2020, I take 2020 to find the T at the end of 2020. I take 2020 minus 2014, I get 186. At the end of 2015, T is 1. We know that 2015 minus 2014 is T is 1 here. So at the end of 2200, to find T, I take 2200 minus 2014, I get 186. So at the end of 2020, or in the beginning of 2201, T is 186. If there won't be another earthquake until 23rd century, means next earthquake occurs from the year 2014 and the end of from the year in the beginning of 2015 to the year 2200. If there won't be another earthquake until 23rd century, means there's no earthquake here. There won't be another earthquake until 23rd century. There's no earthquake here. There's no earthquake here. That means our waiting time must be more than 186 years. If there won't be another earthquake until 23rd century, means there are no earthquake here. Which means our waiting time must be more than 186 years. Our waiting time must be more than 186 years. So X must be more than 186. Waiting time must be 186 or more. When T equal to 186, that's the beginning of the 23rd century, so we must include the endpoint. When T equal to 186, that's the beginning of the 23rd century, so we must include in the endpoint. We must include 186. Then take integral. Suppose from 0 to infinity. If S is greater than 186, that's the integral from 186 to infinity. F of x dx. When S is greater than 186, when S is greater than 186, it satisfies that S is greater than 0. So f of x is 1 over 200 times e raised to negative x over 200. Then take antiderivative. That's negative e raised to negative x over 200. Evaluate from 186 to infinity. If we plug in infinity, e raised to negative infinity is 0. If we plug in 186, we get e raised to negative 186 over 200, which is e, positive e raised to negative 186 over 200. Then use calculator, I get 0.3946. Number 7, part A. Let a probability function f be defined as f of x equal to c over 3 to the power of x for s equal to 1, 2, 3, 4, 5, and so on. Find the value of c and the cumulative distribution function f of 4, the CDF f of 4, the cumulative distribution function f of 4. Let's find c first. We know that f is a probability function. That means f of x must be between 0 and 1 for all x. And the sum of the sum of all x in the support. The sum of all x in the support must be 1. So let's find C based on these two properties. Let's verify the sum first. We want the sum of all x in the support, f of x, to be 1. Here, for the sum of all x in the support, x is 1, 2, 3, 4, 5 until infinity. So take the sum for x from 1 to infinity. F of x is c over 3 to the power of x. This is a geometric theory. It can be rewritten as c times 1 over 3 to the power x. For the sum of geometric theory, the formula is the first term over 1 minus the common ratio. The sum for a convergent geometric theory is the first term over 1 minus the common ratio. Here, common ratio is 1 over 3, so the geometric theory converges. For the first term, for numerator, for the first term, I plug in 1 for x. If I plug in 1 for x, I get c over 3. That's the first term. Over 1 minus the common ratio. Common ratio is 1 over 3. If I multiply the top and the bottom by 3, I have c over 3 minus 1, which is c over 2. And we know that the sum of total probability must be 0, must be 1. So I set c over 2 equal to 1. Then solve an equation for c equal to 2. Then we check. If I plug in c into function f, I get 2 over 3 to the power of x. This is always between 0 and 1. So when c equal to 2, f of x satisfies all conditions for a probability function. So c is 2. Next, find capital F of 4. Capital F of 4 represents the CDF, the cumulative distribution function of 4. So CDF of 4 represents probability that x less or equal to 4. CDF of 4 represents probability that x less or equal to 4. For this function f, f of x equal to c over 3 to the power x, for x equal to 1, 2, 3, 4, 5, and so on. Support of x here is a set of integers from 1 to infinity. Support of x is x from 1 to infinity. So probability that s less or equal to 4, that's f of 1 plus f of 2 plus f of 3 plus f of 4. That's support of x. 1, 2, 3, 4, 5 until infinity. For x less or equal to 4, we choose 1, 2, 3, 4. Then adding up. For f of 1, we plug in 1. I get 2 over 3 to the power 1. For f of 2, I plug in 2 for x. I get 2 over 3 to the power of 2. For f of 3, I plug in 3 for x. I get c over 2 over c is 2. I get 2 over 3 to the power of 3. For f of 4, I plug in 4 for x. I get c over 2 over 3 to the power of 4. Then adding up, I get 81 over 80. That's part A. Part B. Let the probability density function f be defined as f of x equal to c times s squared plus x plus 1 if x is between 6 and 12, and f of x equal to 0 otherwise. Find the value of c, and capital F of 10. Capital F represents the CDF of 10. Part B. This f is a probability density function. It's a PDF. For PDF, there are two properties. That f of x must be greater than or equal to 0. Must always be non-negative. For CDF, f of x must always be non-negative. And the total area under the curve must be 1. The total area under the curve must be 1. Integral from negative infinity to infinity, f of x must be 1. If f is a CDF, it must satisfy these two conditions. If f is a PDF, probability density function, it must satisfy these two conditions. let's try to find C. Let's satisfy both conditions. First of all, let's value for the integral. From negative infinity to infinity, f of x dx. The total area under the curve must be 1. Now, for this function, the support of x is from 6 to 12. Support of x is from 6 to 12. So I take integral from 6 to 12. F of x dx. And when x is between 6 and 12, I use f of x equal to c times x squared plus x plus 1. Then take antiderivative. Take antiderivative. I can pull out c first. If I take antiderivative, I get x over 3, s to the power 3 over 3, plus x squared over 2, plus x. Evaluate from 6 to 12. Then I use my calculator. When I plug in 12, I get 660. When I plug in 6, I get 96. So together, that's 564C. Next, set 564. Set 564C equal to 1. Because the total area under the curve must be 1. So I set 564C equal to 1. Then solve for C. C is 1 over 564. That's C. Next, find f of 10. F of 10, capital F of 10. That's the CDF of 10. Capital F of 10. Since that's the CDF, that's probability that x less or equal to 10. Since support of the function, support of x is from 6 to 12. If x is less than or equal to 10, support of x is from 6 to 12, and probability that x is less or equal to 10, I take integral from 6 to 10. F of x dx. Take integral from 6 to 10, f of x dx. And we know that when x is between 6 and 10, it satisfies the condition that x is between 6 and 12. So I use the function f of x equal to c times x squared plus x plus 1. C times x squared plus x plus 1 dx. Then I can pull out c. Take an antiderivative. If I pull out c, take an antiderivative, I get s cubed over 3 plus s squared over 2 plus x. Evaluate from 6 to 10. Then when I plug in 10, I use my calculator, I get 1180 over 3. And when I plug in 6, I get 96. Here, C is 1 over 564. C is 1 over 564. If I plug in, use my calculator, my final answer is 223 over 423, which is 0.5272. Plug in C, then calculate this. Use my calculator, I get 0.5272. Number A, part A. Let f of x be the PDF of a random variable x. F of x equal to negative x over 6 if x is between negative 2 and 0. F of x equal to s squared if s is between 0 and 1. F of x equal to x squared minus 4x plus 4 if s is between 1 and 2. And f of x equal to 0 otherwise. Find the CDF. We know that the relationship between PDF and CDF is that if we know the CDF, to find the PDF, we take derivative. But to go backward, if we know the PDF, we try to find the CDF, we take antiderivative. So if we know the CDF, to find the PDF, we take derivative. If we know the PDF, to find the CDF, we take antiderivative. So in problem number A, part A here, we know the PDF and we try to find the CDF, so we take antiderivative. If we know the PDF, to find the CDF, we take antiderivative. So this PDF is a piecewise function. This PDF is a piecewise function. Let me first of all draw a number line for the PDF. From -2 to 0. F of x is -x over 6. From 0 to 1, f of x is x squared. Then from 1 to 2, from 1 to 2, f of x is x squared minus 4x plus 4, and 0 otherwise. That means when x is less than -2, f of x is 0. When x is greater than 2, f of x is 0. When x is between -2 and 0, f of x is -x over 6. When x is between 0 and 1, f of x is x squared. When x is between 1 and 2, f of x is x squared minus 4x plus 4. Next, we try to take antiderivative. Here in the number line, we have 5 different regions. 1, 2, 3, 4, 5. There are 5 different intervals. So consider for the antiderivative, consider 5 cases. For the antiderivative, consider 5 cases. Case 1. If x is less than -2, case 1. If x is less than -2, the PDF f of x that's the probability that x less or equal to x. When x is here, the the probability that x is less or equal to x. That's the integral from -infinity to x. F of x dx. From -infinity to x, f of x dx. When s is between -infinity to x, f of x is 0. If we take antiderivative for 0 function, we get 0. So in case 1, if x is less or equal to -2, the CDF f of x is 0. Case 2, if x is between -2 and 0, the CDF f of x is probability that x less or equal to x. That's from -infinity to x, f of x dx. Case 2, s is here. Case 2, s is here. From -2 to 0, s is here. So the integral from -infinity to x has 2 pieces here. Integral from -infinity to x has 2 pieces. First piece is from -infinity to -2, f of x dx, plus second piece from -2 to x, f of x dx. Then from -infinity to -2, from negative infinity to negative 2, f of x is 0. From negative 2 to x, f of x is negative x over 6. Dx. We know that integral of 0 is 0. Integral of 0 is 0. Next, for the second integral here, take antiderivative. Take antiderivative for negative x over 6. I get negative x squared over 12. Evaluate from negative 2 to x. If I plug in x, it stays the same. If I plug in negative 2, negative 2 squared is 4. 4 over 12 is 1 over 3. So I get negative 1 over 3. Simplify, that's 1 over 3 minus x squared over 12. So if x is between negative 2 and 0, the CDF f of x is 1 over 3 minus x squared over 12. That's case 2. Case 3, x may be between 0 and 1. Case 3, when s is between 0 and 1, s is here. Case 3, s is between 0 and 1, s is here. The CDF f of x is probability that x less or equal to x from negative infinity to x. F of x dx. Here, from negative infinity to x, we have 3 pieces. First piece, x is between negative infinity and negative 2. Second piece, s is between negative 2 and 0. Third piece, s is between 0 and x. If x is from negative infinity to x, we have 3 pieces. So first piece, from negative infinity to negative 2, f of x dx. Second piece, from negative 2 to 0, f of x dx. The third piece, from 0 to x, f of x dx. The first integral, from negative infinity to negative 2, f of x is 0. The second integral, from negative 2 to 0, f of x is negative x over 6 dx. The third integral, from 0 to x, f of x is x squared dx. Then take antiderivative. First integral, we know from the previous part, is 0. Second integral, take antiderivative. We get negative x squared over 12. Evaluate from negative 2 to 0. Third integral, take antiderivative. I get s cubed over 3. Evaluate from 0 to x. For the second integral, if I plug in 0, I get 0. If I plug in negative 2, negative 2 squared is 4. 4 over 12 is 3, is 1/3. Negative 1/3. So this is positive 1/3. The third integral here, if I plug in x, it stays the same. If I plug in 0, I get 0. So together, I have 1/3 plus x over 3. Together, I have 0 plus 1/3 plus x over 3, which is 1/3 plus x over 3. That means if x is between 0 and 1, the CDF f of x is 1/3 plus x over 3. 1/3 plus x cubed over 3. That's the CDF if s is between 0 and 1. Now case 4. Case 4. If s is between 1 and 2. Case 4. If s is between 1 and 4. If s is between 1 and 2, from net infinity to x, we have 1, 2, 3, 4. We have 4 pieces. The CDF f of x is the probability that x less or equal to x, which is the integral from net infinity to x, f of x dx. From net infinity to x, there are 4 pieces. First piece from net infinity to negative 2. Second piece from negative 2 to 0. Third piece from 0 to 1. And the fourth piece from 1 to x. So there are 4 pieces. There are 4 different pieces. For x between negative infinity and negative 2, f of x is 0. For x between negative 2 and 0, for x between negative 2 and 0, f of x is negative x over 6. For x is between 0 and 1, for x is between 0 and 1, f of x is s squared. For x between 0 and 1, f of x is s squared. For x between 1 and x, for x between 1 and x, f of x is x squared minus 4x plus 4. Between 1 and x, f of x is x squared minus 4x plus 4. Dx. Then take antiderivatives. We know that from the previous part, integral from negative infinity to negative 2 is 0. Integral from negative 2 to 0. Integral from negative 2 to 0 is 1/3. For integral from 0 to 1, I take antiderivative here. I get x cubed over 3. Evaluate from 0 to 1. If I plug in 1, I get 1/3. If I plug in 0, I get 0. For the last integral, take antiderivative. I have s cubed over 3 minus 2s squared plus 4x. Evaluate from 1 to x. If I plug in x, everything stays the same. I get s cubed over 3 minus 2s squared plus 4x. If I plug in 1, I get 1/3 minus 2 plus 4. One-third minus 2 plus 4. That's 7 over 3. So together I have 0 plus 1/3 plus another 1/3 plus this. 0 is nothing. 1/3 plus 1/3 minus 7/3 is minus 5/3. This part stays the same. S cubed over 3 minus 2s squared plus 4x minus 1/3 plus 1/3 minus 7/3 is negative 5/3. That's the CDF. That's f of x if x is between 1 and 2. Case 5. Case 5. If x is greater than 2. If s is greater than 2, s is here. If s is greater than 2, s is here. So CDF f of x is probability that x less or equal to x. That's the integral from negative infinity to x. F of x dx. If s is here, for the integral from negative infinity to x, we must consider one piece, two piece, a third piece, the fourth piece, and the fifth piece here from 2 to x. So consider these 5 pieces here, from negative infinity to negative 2, from negative 2 to 0, from 0 to 1, and from 1 to 2, and from 2 to x. From negative infinity to negative 2, from negative 2 to 0, from 0 to 1, from 1 to 2, last piece from 2 to x, f of x dx. And then we know that when s is from negative infinity to negative 2, f of x is 0. When s is from negative 2 to 0, f of x is negative x over 6. When s is from 0 to 1, f of x is s squared. When s is from 1 to 2, f of x is s squared minus 4x plus 4. And when s is from 2 to x, when s is from 2 to x, f of x is 0. From the previous part, now we need to solve the integral. From the previous part, we know the first integral is 0. The second integral is 1/3. The third integral is also 1/3. We don't know the fourth integral, but the last integral of 0 is always 0. The last integral of 0 is always 0. Now let's solve the fourth integral here. I first of all take an antiderivative. I get s cubed over 3 minus 2s squared plus 4x. Evaluate from 1 to 2. If I plug in 2, I get a over 3 minus a plus a. If I plug in 1, from the previous part, if I plug in 1, I know that I get 7 over 3. If I plug in 1, I get 7 over 3. Here, negative a and positive a can cancel. A over 3 minus 7 over 3 is 1 over 3. So together we have 0 plus 1/3 plus 1/3 plus 1/3 plus 0. 1/3 plus 1/3 plus 1/3 is 1. That means if s is greater than 2, f of x is 1. If s is greater than 2, f of x is 1. So for the final answer, write it as a piecewise function. The CDF f of x is, first of all, is 0. F of x is 0 if x is less than -2. Case 2. F of x is 1/3 minus x squared over 12 if x is between -2 and 0. Third piece. If s is between 0 and 1, f of x is x cubed over 3. If s is between 0 and 1, f of x is 1/3 plus s cubed over 3. If s is between 0 and 1, f of x is 1/3 plus s cubed over 3. Case 4. If s is between 1 and 2, f of x is s cubed over 3 minus 2s squared plus 4x minus 5 over 3. So f of x is s cubed over 3 minus 2s squared plus 4x minus 5 over 3 if s is between 1 and 2. Last piece. If s is greater than 2, f of x is 1. So f of x equal to 1 if s is greater than 2. That's part A. That's number A, part A. Now for number A, part B. Let capital F be the CDF of a random variable x. That's the CDF. F of x equal to 0 if x is less than or equal to -1. F of x equal to s squared over 2 plus x plus a half if s is between -1 and 0. F of x equal to -s squared over 2 plus x plus a half if s is between 0 and 1. And f of s equal to 1 if x is greater than 1. If s is greater than or equal to 1. Find the PDF. Find the PDF. We know that if we know the PDF, we try to find the CDF, we take antiderivative. If we know the CDF and we try to find the PDF, we take derivative. If we know the CDF and we try to find the PDF, we take derivative. Here, this capital F represents the CDF. If we know the CDF and we try to find the PDF, we take derivative for the PDF. Take derivative for the PDF. Let me first of all draw a number line. If x is less than -1, f of x is 0. If s is between -1 and 0, f of x is s squared over 2 plus x plus half. Third piece, if s is between 0 and 1, f of x is negative s squared over 2 plus x plus half. And the last piece, f of x is 1 if s is greater than or equal to 1. Those are PDF. This is PDF. We know that from PDF from this is CDF. If we know the CDF, to find the PDF, we take derivative. Those are the CDF. If we try to find a PDF, we take derivative. Derivative of 0 is 0. Derivative of s squared over 2 plus x plus half. That's x plus 1. Derivative of negative s squared over 2 plus x plus half. That's negative x plus 1. And derivative of x is 0. Derivative of 1 is 0. Derivative of 1 is 0. So for the CDF, for the PDF, f of x, we have f of s equal to s plus 1 if s is between negative 1 and 0, equal to negative x plus 1 if s is between 0 and 1, 0 otherwise. When we run the PDF, in the interval, we don't include the endpoints. We don't include the endpoints because for piecewise function, in general, for piecewise function, in general, there's an angle, or there's a sharp angle, there's an angle or corner in the boundary. For piecewise function, usually there's a sharp angle on the corner in the boundary. And at this point, usually the function is not differentiable. So we don't include endpoints. If we know the CDF and we try to find a PDF, and when we take derivative, we don't include the endpoints because an endpoint usually is not differentiable. There's sharp angle here. It's not differentiable. So I set equal to 0. At the boundary point, we set f of x equal to 0. At the boundary point, we set f of x equal to 0. So when we use CDF to find a PDF, and when we take derivative for the final answer, we don't include the endpoint for every intervals. Number 9. Let the CDF of a random variable x be defined as the following graph. So suppose this graph represents a CDF. This graph is y equal to capital F of x, the CDF. Find each of the following probabilities. Part A, probability that x equal to negative 2. Part B, probability that x less than or equal to negative 1. Part C, probability that s less than 0. Part D, probability that s greater than or equal to 2. Part E, probability that s is between negative 2 and 2, including negative 2. Part F, s is between negative 2 and 0, not including the endpoints. Now, if we try to use the CDF to find probabilities, try to rewrite the probability in the form of probability that s less or equal to some number. If we try to use the CDF to find the probabilities, try to rewrite each probability in the form of x less or equal to some number, or probability that x less or equal to some number. Because probability that x less or equal to a is CDF f of a. Probability x less than a, x strictly less than a, that's the probability that's CDF f of a, take limit from left side. So probability that x less or equal to a is CDF f of a. Probability that x strictly less than a, that's CDF f of a, take limit from left side. And for these values, we can find it from the table, from the picture. So we try to write each probability in its two forms first. In order to use CDF to find probabilities, we need to rewrite each probability in this form, in the form of probability that x less or equal to a, and probability that x strictly less than a. Part A, probability that x equal to -2. We try to put it in this form. How can we do that? Probability that x equal to -2, I can write it as probability that x less or equal to -2, take away probability that x less than -2. Probability that x less or equal to -2, take away probability that x less than -2. That's probability that x equal to -2. Because here, probability that x less or equal to -2, that means either x is less than -2 or x is equal to -2. If I remove x less than -2, what's left is probability that x equal to -2. So probability that x equal to -2 can be written as probability that x less or equal to -2 minus probability that x is less than -2. So here, probability that x less or equal to -2, that's CDF f of -2. Probability that x less or equal to -2, that's a CDF f of -2. Probability that x strictly less than -2, that's CDF f of -2, but we'll take limit from left side. Now I can read it from the table. F of -2, f of -2. For f of -2, look at the starting point. Starting point is here, which is 0.4. F of -2 from take limit from left side. F of -2 take limit from left side. Left side limit approach to 0.2. So 0.4 minus 0.2 is 0.2. That's part A. Part B. Part B. Probability that x less or equal to -1. That's in this form. That's in this form already. So this is capital F of -1. This is capital F of -1. Capital F of -1, I can read it from table. Capital F of -1 is here. That's 0.4. Next, part C. What's probability that x is less than 0? Probability that x is less than 0, that's in this form. X less than as a constant, strictly less than a constant. That's the CDF f of 0, take limit from left side. CDF f of 0, take limit from left side. 0 is here. Limit from left side is 0.4. Limit from left side is 0.4 here. Part D. What's the probability that x is greater than or equal to 2? For probability that x is greater than or equal to 2, we try to put it in the form that probability is less than some constant. So for x is greater or equal to 2, think of the complement. This can be rewritten as 1 minus probability that x is less than 2. Probability that x is less than 2, that's in the form of probability x less than a constant. So I take CDF f of 2, take limit from left side. F of 2, limit from left side. 2 is here. Limit from left side is 0.8. 2 is here. Limit from left side is 0.8. 1 minus 0.8 is 0.2. Part E. Probability that what's the probability x is between -2 and 2, including -2. Part E, find the probability that x is between -2 and 2, including -2, not 2. Probability that x is between -2 and 2, including -2, but not 2. So, how do we write this probability in this form? we can think of a number line from -2 to 2. We're looking for this part. Here, what we can try is take the entire line, probability that x less than 2. The entire line is probability that x less than 2. Take the entire line, remove this piece. The entire line is probability that x less than 2. The entire line is x less than 2. If I remove this piece, since I try to keep -2 here, so I don't remove -2. If I take the entire number line here from -infinity to 2, remove this piece, x less than -2, what I get is here, s between -2 and 2. If I take this, remove x less than -2, what's left is s between -2 and 2. Since I don't remove -2, -2 stays here. So this can be rewritten as probability that x less than 2, remove probability that x less than -2. Then this can be rewritten as CDF f of 2 from left side. That can be rewritten as CDF f of -2 from left side. F of 2 from left side, 2 is here. Limit from left side is 0.8. Minus f of -2 limit from left side. -2 is here. Limit from f of -2 limit from left side is here, which is 0.2. 0.8 minus 0.2 is 0.6. That's the probability that x is between -2 and 2. Part F. Probability that x is between 0, s is between -2 and 0. Probability that s is between -2 and 0, not including the endpoints. Same thing. I can first of all draw a number line from -infinity to 0. This line represents x less than 0. What we try to find is x between -2 and 0. So -2 is here. We try to keep this piece. If I try to keep this piece, I need to remove this piece here. This piece contains all points that x is less than -2, less than or equal to -2. Since I don't want to keep -2 here, what I want is s between -2 and 0, not including -2. So that means I need to remove -2. If I remove x less than or equal to -2, what's left is this line segment from -2 to 0, not including -2 and 0. So this probability can be rewritten as probability that x less than 0, the entire line, minus probability that x is less than or equal to -2, this piece here. Probability that x less than 0, that's the CDF f of 0 from left side. Probability that x less than or equal to -2, that's the CDF f of 2. Then f of 0 from left side, look at the picture, 0 is here. Limit from left side is 0.4. Minus f of -2. For f of -2, look at the solid point. F of -2, the solid point is here, which is also 0.4. 0.4 minus 0.4 is 0. Number 10. A bag contains 3 red marbles, 5 blue marbles, and 7 green marbles. When 4 marbles are randomly selected from the bag, the X represents the number of red marbles. Part A, find the expected value of x and the variance of x. Part B, find the expected value of 2x squared plus 3x minus 1 and the variance of 4x plus 2. So first of all, let's find the probability function first. Let's first of all find the probability function first. In order to find the expected value and variance, let's find the probability function first. First of all, try to recognize what kind of probability distribution it is. First of all, try to recognize what kind of probability distribution it is. A bag contains 3 red marbles, 5 blue marbles, and 7 green marbles. When 4 marbles are randomly selected from the bag, X represents the number of red marbles. We can consider red marble as success, and the rest, blue marble and green marble, as failure. We can consider red marble as success, blue marble and green marble as failures. And when we choose marbles, every time the probabilities since we don't replace the marble back, the probability is not the same for every choice. So this is hypergeometric distribution. We won't choose marbles without replacement. If we don't replace the back, probability for each choice is not the same. So here we use hypergeometric distribution. X has a hypergeometric distribution. We consider red marble as success. We have 3 red marble. We consider blue marble and green marble as failures. Here we have 12 failures. And we are choosing 4 marbles. We have 4 trials. N is 4. Then write down the formula. Probability function for hypergeometric distribution is N1 choose x, N2 choose n minus x, over N1 plus N2 choose n. If I plug in N1, N2, and n, I have 3 choose x, 12 choose 4 minus x, N1 plus N2 is 15, choose n is 4. That's the probability function. Next, try to find the support. Find maximum of 0 and n minus n2. M minus n2 is 4 minus 12. 4 minus 12 is negative a. So maximum of 0 and negative a is 0. Next, find the minimum of n and n1. Next, find the minimum of n and n1. N is 4, N1 is 3. Minimum of 4 and 3 is 3. So the support of x. Support of x is integers from 0 to 3. Next, we try to compute f of 0, f of 1, f of 2, f of 3. Try to compute f of x for all x in the support. Next, try to compute f of x for all x in the support. F of 0 is 3 choose 0, 12 choose 4, over 15 choose 4. F of 1 is 3 choose 1, 12 choose 3, over 15 choose 4. F of 2 is 3 choose 2, 12 choose 2, 15 choose 4. F of 3 is 3 choose 3, 12 choose 1, and 15 choose 4. And here I use my calculator. I get f of 0 is 33 over 91. F of 1 is 44 over 91. F of 2 is 66 over 455. F of 3 is 4 over 455. Then for the expected value e of x. That's the sum of all x in the support. X times f of x. The sum of all x in the support. X times f of x. So here, for x in the support, we have 0, 1, 2, 3, which is 0 times f of 0 plus 1 times f of 1 plus 2 times f of 2 plus 3 times f of 3. F of 0 is 33 over 91. F of 1 is 44 over 91. F of 2 is 66 over 455. F of 3 is 4 over 455. Then I use my calculator. If I add them up, I get 4 over 5, which is 0.8. Next, we try to find the variance of x. We know that variance of x is e of x squared minus e of x squared. So let's compute e of x squared first. For e of x squared, take the sum for all x in the support. Let x squared times f of x. The sum of all x in the support of x squared times f of x. So x in the support, we have 0, 1, 2, 3. For all x in the support, we have 0, 1, 2, 3. So if I plug in, I have 0 squared times f of 0 plus 1 squared times f of 1 plus 2 squared times f of 2 plus 3 squared times f of 3. 0 squared is 0. F of 0 is 33 over 91. 1 squared is 1. F of 1 is 44 over 91. 2 squared is 4. F of 2 is 66 over 455. 3 squared is 9. F of 3 is 4 over 455. Then here, this calculator. I use calculator and add them up. I get 8 over 7. When I use calculator adding up, I get 8 over 7. So for variance of x, I use e of x squared minus e of x squared. E of x squared is 8 over 7. E of x squared. E of x here is 4 over 5. Then use calculator. 8 over 7 minus 4 over 5 squared. I get 88 over 175. So that's expected value of x. That's the variance of x. That's part A. That's number 10, part A. Part B. Find the expected value of 2x squared plus 3x minus 1 and the variance of 4x plus 2. Let's find the expected value first. For expected value of 2x squared plus 3x minus 1, I can rewrite its expectation as 2 of expected value of x squared plus 3 times expected value of x plus negative 1, that means minus 1. And then from the previous part, we know e of x squared, expected value of x squared is 8 over 7. Expected value of x is 4 over 5 minus 1. Then I use my calculator, I get 129 over 35. That's the expected value. Next, find the variance. Find the variance of 4x minus 2. Find the variance of 4x minus 2. For variance of 4x plus 2, I pull out the coefficient of x and square this number. 4 times variance of x. The constant disappear. 4 square times variance of x. Constant disappear. 4 square is 16. Variance of x. From the previous part, we know that variance of x is 88 over 175. Then use calculator. Use my calculator, I get 1408 over 175. Number 11. Let x be a random variable with x has a uniform distribution from 44 to 55. So here x has a continuous uniform distribution from 45 to 55. X has a continuous uniform distribution from 45 to 55. Part A, find the expected value of x and the variance of x. Part B, find the expected value of x cubed and the variance of x squared. So first step, let's write down the probability density function, the PDF of f of x. First step, let's find the PDF of x. We know that for uniform distribution, the PDF is 1 over beta minus alpha if s is between alpha and beta, and f of x equal to 0 otherwise. Here in this problem, x is uniform distribution from over the interval from 45 to 55. X has a uniform distribution over the interval from 45 to 55. So that's alpha, that's beta. 45 is alpha, 55 is beta. So plugging alpha and beta. Beta is 55, alpha is 45. 55 minus 45 is 10. Alpha is 45. Beta is 55. And next, find the support of x. Find the support of x. For continuous uniform distribution, support of x is the closed interval from alpha to beta. For continuous uniform distribution, support of x is in a closed interval from alpha to beta. Alpha is 45, beta is 55. So the support of x is in a closed interval from 45 to 55. Next, based on this, answer the question. Part A, find expected value and the variance of x. For expected value of x, that's the integral from negative infinity to infinity. X times f of x dx. Expected value of x is the integral from negative infinity to infinity. X times f of x dx. And here, support for x, the support is from 45 to 55. The support is from 45 to 55. So take integral from 45 to 55. X times f of x dx. When s is between 45 and 55, it satisfies the condition here. So we use f of x equal to 1 over 10. X times 1 over 10 dx. If I take antiderivative, I have x squared over 2 times 1 over 10. Evaluate from 45 to 55. That can be written as 1 over 20 times 55 squared minus 45 squared. And here I use my calculator. I get 50 in my calculator. Next, find the variance of x. we know that variance of x is expected value of x squared minus expected value of x squared. So let's compute expected value of x squared first. Expected value of x squared, that's the integral from net infinity to infinity. X squared times f of x dx. And support of x is from 45 to 55. Support of x is from 45 to 55. So I take integral from 45 to 55. X squared times f of x. For x between 45 and 55, it satisfies the condition here. So we use f of x equal to 1 over 10. Then take antiderivative. I get s cubed over 3 times 1 over 10, which is 1 over 30 times evaluate from 45 to 55. That's 1 over 30 times 55 cubed minus 45 cubed. Here I use my calculator. I get 7,525 over 3. Next, for variance of x, we use e of s squared minus e of x squared. Expected value of x squared minus expected value of x squared, which is 7,525 over 3 minus 50 squared. And again, I use my calculator here. I get 25 over 3. That's variance of x. Part B. Find expected value of s cubed. Find expected value of s cubed. Expected value of s cubed. That's the integral from net infinity to infinity. S cubed times f of x dx. Support of x is from 45 to 55. So take integral from 45 to 55. S cubed times 1 over 10. Then take antiderivative. Take antiderivative. I have x to the power 4 over 4 times 1 over 10. Evaluate from 45 to 55. Which is 1 over 40 times 55 to the power 4 minus 45 to the power 4. And again, I use my calculator here. I get 126,250. That's expected value of s cubed. That's expected value of s cubed. Next, I'm trying to find variance of s squared. We try to find variance of s squared. For variance of s squared, we try to compute expected value of x squared squared minus expected value of s squared squared. That's variance of s squared. Expected value of s squared squared minus expected value of s squared outside the parentheses. Let's compute expected value of s squared squared first. Expected value of x squared is x to the power 4. Expected value of x to the power 4. X squared is x to the power 4. Let's integral from negative infinity to infinity. X to the power 4 times f of x dx. Since support of x is from 45 to 55, take integral from 45 to 55. X squared x to the power 4 times f of x dx. And when s is between 45 and 55, it satisfies the condition that s is between 45 and 55 here. So I can use f of x equal to 1 over 10. S to the power 4 times 1 over 10 dx. Then take an antiderivative. I get x to the power 5 over 5 times 1 over 10. Evaluate from 45 to 55. That's 1 over 50 times 55 to the power 5 minus 45 to the power 5. Then here I use my calculator. When I use my calculator, I get 6,375,125. That's expected value of x to the power 4. Then, for variance of x squared, I use expected value of x to the power 4 minus expected value of x squared. Expected value of x to the power 4, we just found it. That's 6,375,125 minus expected value of x squared. Expected value of x squared is 7,525 over 3. Expected value of x squared is 7,525 over 3. 7,525 over 3 squared. Then again I use my calculator. I get 750,500 over 3 over 9. That's the final answer.